All right, we're going to get started. Reilly's a computer science student, been working in the visualization lab for 2.5 years now. Jay's going to present his defense on visualizing soundscape results.
All right, thank you. So, hello everybody, my name is Reilly Lessard. I'll be defending my thesis titled Quantifying Contributions of Sonar Systems on Marine Soundscapes, a Statistical and Machine Learning Analysis. So, for a little bit of background information, soundscapes are characterized by a number of both biotic and abiotic features. Biotic can include fish, grunts, whale vocalizations, some snapping shrimp. Abiotic features can be anything from geological activity or rain, sometimes anthropogenic sound. So that can also include motorized vehicles, so jet skis, larger or smaller vessels, industrial activity, which can include pile driving or gas and oil mining, sonar operation that can include both ocean mapping and military and any other sonar that might be there. Another thing to consider is propagation of sound. So obviously, the further away something is, the quieter is going to appear in a soundscape, but that doesn't necessarily change how important it is. The soundscape metrics are the main thing that I used for this analysis. So uniformity is one measurement, which is quantified using dissimilarity. That is essentially measuring shifts in the frequency composition. So measuring how different does soundscape change from one moment to another. In this case, minutes are used. Impulsivity, kurtosis is how this is quantified, essentially measuring the sharpness or sudden sounds. So if the soundscape were to be relatively uniform, it sounds about the same, regardless of volume, basically. How much does it change? So an immediate change in the soundscape would be a sharp increase in kurtosis. Periodicity, beat count is how this is measured, and that is essentially the number of high-intensity sounds, sometimes how repetitive the soundscape appears to be. Amplitude, this uses both sound pressure level, root mean square, and peak. And this is the historically most popular way to measure a soundscape, but it isn't the only way to quantify it. And the reason that RMS and peak are both used is because RMS can be typically used for more long-term analysis, trying to find the general trends, versus the peak, which can find immediate changes and these very large values that may stand out and change the average or median. Calculated with soundscape code. So this was code that was provided to me, and the input parameters can be simply added to the code and the numbers will be made quite easily. Some of the concerns, a little bit of the reason for this research. So some marine mammals have been observed to behave differently when exposed to anthropogenic activity. One example is a study of bowhead gray whales, which were noticed to avoid continuous sounds at about 120 decibels. And in this particular study, it wasn't universal. Not every whale did change the same. Not all of them did change their habit at all. Sometimes they were the same throughout. Another study, the North Atlantic gray whale, around 20 or 200 hertz. Some ship traffic did disturb them, but again, wasn't always the case for every single individual whale observed. Vocalization frequency increase and stress hormone increase were two observed changes. And the Marine Mammal Protection Act, MMPA, was made decades ago to try to minimize the impact of acoustic impulses and continuous sounds caused by industrial sounds. Changes in animal behavior. Impulsive sounds have been noticed to be a larger contribution to animals' behaviors, and we want to essentially minimize how much we do change their behaviors. Habitat degradation. Over time, it can be a big impact versus if you were to look at day by day, you may not see a huge change, but over months or years, you will potentially see some changes. Temporary and permanent threshold shifts. This can be a little tricky to measure because in doing so, you're essentially trying to harm these animals by trying to find out the exact thresholds, either the time it takes for exposure to kick in, or for any threshold shift to change, or if there's a certain frequency that might hurt them, anything related to that. Ocean mapping sonar systems. The two systems used were the Kongsberg TOPAS PS40 and the RESON SeaBat T51-R. The PS40 is a single beam sublimic profiler operating at 35 to 45 kilohertz. And one of the benefits to this is that it can be used to find both the ocean floor and some of the sediment below what it's made out of. The T51-R is a multibeam echosounder operating at about 800 kilohertz. And one thing to note is that 800 kilohertz was too high for my recorders to actually record, but its indirect impact or contributions can still be observed. And what they do, what the exact impacts of these two systems are not fully known yet, and trying to fully quantify them can be a little bit tricky and can't be necessarily generalized to every other sonar system. Machine learning models. So the two models that are used are a CNN and a transformer. And these are two relatively popular architecture models. The CNN mainly tries to focus on more short-term patterns using convolution, looking at 1 minute, comparing it to its nearby neighbors, versus the transformer, which is able to compare every single record to every other record. So computationally, it is more expensive, but the results can potentially reveal any long-term patterns that may exist in the data. What are the main goals? Assess changes in the marine soundscape relative exposure periods for both the PS40 and the T51-R, looking at the more statistical analysis, whereas the machine learning analysis comparing the CNN and the transformer to find out if it can predict the relative exposure period since the most recent exposure, using the soundscapes as inputs along with temporal and spatial data, including time of day, day of the week, and distance from the recorder. What were the two main hypotheses? The first alternative hypothesis would be that both the T51-R and the PS40 would have significant contributions to impulsivity and amplitude, at least at ultra high frequency, which is anything above 10,000 hertz. The second alternative hypothesis was expecting that the transformer would yield better results, essentially getting higher accuracy than the CNN, due to the transformer's attention mechanism, which makes it able to find these long-term patterns in the data. Methodologies. Some of the logistics was mainly planning the deployments, which mainly required making the right parameters for the deployments. So having a sampling rate, if it was going to be a continuous recording or on and off for different periods of time. The machine learning, again, using the soundscape metrics as the input along with spatial and temporal data, and using both the CNN and transformer, which both had roughly the same architecture layers, with the difference being the convolution in the CNN and the attention mechanism of the transformer. But otherwise, they were roughly the same thing. Selecting locations. So what you see on the left is for the PS40 deployment. There were a couple different locations that were potential places to deploy it. It was decided that the northern sand body would be the location. Reason being that it has a roughly sandy floor, which is definitely desirable compared to a more rocky floor, which the anchor it was attached to would generate extra noise, scratching back and forth. That would create extra noise, making the data set almost unusable. The two different locations, so A, you can see was where the PS40 recorder was placed at, and B was for the T51-R. PS40 was in operation on April 9th when it was directly overhead, and the recording was entirely from April 6th to May 31st of last year. The recording frequency of the sound trap was 96 kilohertz. It was at about 22 meters, and the noise from the anchor settling was during the initial hours. Within 10 or 12 hours, it was able to settle properly for the recordings, but that still provided some amount of pre-exposure data. For the T51-R, the recording was June 1st, August 13th, but during mid or late July, that was when you could hear a scratching in the recording, and when the sound trap was recovered, it was revealed that the anchor rope was attached around the anchor, so that created extra noise. So a couple weeks of recording was pretty much unusable and could not be used for training and testing the models. The recording, even though it was higher than the first recording, 192 kilohertz, it still wasn't high enough to record the T51-R, which operated well above that at 800 kilohertz. And you can see the polygon surrounding figure B. That was where Summer Hydro's main surveying took place. It's all off the Gulf of Maine, so you can see like Newcastle in the top right for reference. Data collection. So I mentioned the sound traps. What are they? They are hydrophones, which are essentially underwater microphones. And depending on the parameters for recording, they can record for up to about 6 months, depending on the batteries and the recording frequency. But that is if you were to do a very low frequency and if the temperature of the water itself was at the right amount. And they were both used for the PS40 and the T51-R. So for what this image is essentially showing, you can see the two cylinders, which are what the hydrophones are, attached to the anchor, which has rope attached to it. So a buoy can be placed at the top of the rope so you know where it is, so you can retrieve it easily. The two sonar systems recorded. So Kongsberg TOPAS PS40 and the SeaBat T51-R. So in just a second, you'll hear what it sounds like, the PS40. Okay, might not work then, but you can essentially hear clicking of the PS40. And this was when the PS40 was directly overhead the recording. So you can see exactly when it's happening. So the image of the spectrogram is essentially showing a fraction, like basically a second of a recording spread out. So you can see each individual ping along with the waveform corresponding to each of those pings. So the PS40 was in operation on April 9th, as I mentioned. And the T51-R, as a part of summer hydro, taking place over the course of about 3 weeks from June 11th to June 27th, on and off. So there's multiple exposure periods, so during and after. Moving averages are one way to easily find patterns in long-term data sets. So amplitude, impulsivity, uniformity, periodicity. What you're looking at right now is the data set from summer hydro. And each of these yellow bars is when the T51-R was in operation. So if there were any immediate changes in the soundscape, you would see them lining up perfectly with these changes in the metrics. But you don't really see a whole lot of changes except for an amplitude, really, which can be expected because that's essentially measuring the loudness of the soundscape, more or less. Analysis. So statistical and machine learning. What you can see along the bottom is line plots from the PS40 exposure. So you have before, which is 25.5 to 22.5 hours, or the day before initial exposure. Red during, so 90 minutes before to 90 minutes after. And what you can see, the vertical black dotted line is when it was direct overhead. So you can see sound pressure at the peak. There was definitely a change in that, which could be directly because of the PS40 or potentially because of the ship it was attached to, which is also generating noise passing by. The blue, the day after, which is 22.5 to 25.5 hours after. You can definitely see before and after sound pressure level is roughly the same versus during, again, it could be related to the boat instead of just the PS40 itself. Right here is essentially an example of what happens in machine learning training for a neural network. So it starts off gaining a lot of accuracy, growing very fast, and it reaches a certain point where the assigned weights for those metrics do not tend to increase much better. So right here you see for the test accuracy, at about 50%, it starts to level off. It's not going to get much better after that. Statistical analyses. So box plots are a great way to find more qualitative data, so along with the line graphs. You can see the general trends in the data set. So what you can see here is essentially each frequency range, low, mid, high, and ultra high, looking at both before, during, and after exposure. You can definitely see, at least for sound pressure level, during exposure, it is louder because the ship is in close proximity. It's also creating noise, but it's also hard to distinguish and say, this is definitely the PS40, this is definitely the T51-R. Could be a number of other features. Minimums, medians, and maximums, those are another way to use a heat map to find more quantitative data along with analyses of variance. Machine learning analysis. So acoustic metrics were used as the input data for these. So each metric was used as a different dimension for the input. The CNN and transformer were the two models evaluated. In evaluation, a lot of very specific data came from this. So training and test loss was used, confusion matrices, F1 score, and precision and recall. So this number plot can basically be a little bit overwhelming. Essentially what you need to focus on is the bright red colors. So during exposure of the PS40 and the ultra high frequency, at the frequency that it operated. You can see the bright red colors, which are essentially saying, here is when the numbers were the most extreme, more or less. And because it's the maximums, they can kind of be ignored. You mostly want to look at the medians because those are the more overall trends in the data set. And between exposure periods, you see roughly the same colors corresponding to roughly the same information, with the real change being in peak count. The median, 89.5. It's kind of high, but it is a very repetitive sound in the soundscape, so that is something that can be expected. Blue line plots. So again, you're looking at before, during, and after, and you can definitely see sound pressure, peak and RMS, and peak count. You can see maybe changes in the soundscape corresponding to initial exposure. Dissimilarity in kurtosis, not as distinguished, but you can see a little bit in dissimilarity, a little lower and more plain before and after, during, kinda, but not perfectly aligned with the initial exposure. And that's in both the ultra high and high frequency. Not too much crazier than the ultra high frequency. Box and whisker plots were a great way to find general trends. So during exposure, you see some more outliers in the data set, especially in peak count. You can see at the high and ultra high frequency, some very high values corresponding there. Not so much in the other metrics for that. So ANOVA is another great way to use this information. So a low p-value essentially is saying that the information is statistically significant compared to before and after exposure versus where you're looking at during exposure.
Laura has a question.
Yeah.
Hey, sorry. I was usually I barged right in, but I wasn't allowed to. And I was like, what's up with that? Sorry. Can you go 2 slides back where you had the min-max, or like this one also works, right? So just so I understand this right, and remember vaguely we talked about this one before. So in the during event, you have higher amplitudes, but that's also because, well, you measure the event, you measure your signal, not your stimulus, not just the response. Is that right?
What do you mean? Sorry.
So well, here like the red lines, this is like sound during the event.
Correct.
Right. So but your event is a sound event, like you put in some noise. So
yeah.
You see a higher amplitude in during because you see the noise that's being put out. This is not like the reaction of the soundscape to the signal. It's like both of those together.
Right, so it's both the ship and the PS40 at the same time.
Okay. Okay. So the main test point is like before versus after, because the during is like polluted by your signal.
Yeah, so ideally you would see no ship noise. You would hear just the PS40, but in that case,
it's not realistic. Yeah, it's just
we just couldn't have that.
Okay, sure. Thanks.
Yeah. Okay. And the T51-R, you don't see the same points as from the PS40. The kurtosis and SPL PK are not during exposure. You actually see them before. And you don't see all the same trends in this data, even though you're still looking at the ultra high frequency, which could be because the T51-R was operating at frequency too high to record. So again, looking at before, during, and after, we're looking at either the ultra high or the high frequency. During initial exposure, you don't see immediate changes. It doesn't correspond to that exact time. Really, the only big takeaway from this that I could find, it was during kurtosis. 24 hours before, you see some higher values, versus during and after, it seems to level off. But for other 4 metrics, don't see too immediate changes. So, peak count and kurtosis. Again, if you see the ultra high frequency, that's where you find any real interesting information. But low, mid, and high, roughly all the same values pretty much. Again, looking at ANOVA, you see a lot of low p-values corresponding to their higher f values, with the difference being in mid-frequency for RMS. And the reason I looked at RMS is because that's still the more typical metric that's used, as opposed to the others used. Machine learning. little bit of recap. How neural networks work is they have an input layer where they're basically reading the data, so the soundscape metrics. It's fed into one or more hidden layers, which try to assign different weight values to each of these metrics, saying, okay, is this one more important? Is this one less? Does this one have a negative impact, perhaps? Given to that output, says, okay, here's what the accuracy is. Let's try this again with different weight parameters. See if we can improve it. You see an increase in accuracy from a weight parameter change. That's good. You want to try it, maybe slim it down, try to refine it even more so. And it goes through different iterations to find the best accuracy you can find until it essentially finds no improvement between epochs. Loss in accuracy. On the left, loss, so you ideally want to see that be as low as possible, and accuracy on the right be as high as possible, but it tended to plateau at about 50 or 55%. And during training, it's essentially trying to learn from all the data input, and the test is when it's saying, okay, here's data we haven't seen yet, how accurate are we still?
So can I ask another question here? So you said
Sure.
Accuracy plateaus at 50%. So if your data set would be balanced between the yes and the no's, that would be pretty bad. That would be like random guessing. But your data set is probably not.
Yeah, so it isn't a binary input. It's essentially classification for different exposure periods, which I actually have on the next slide, so I can.
Okay, sorry, go there. I'll be patient.
Okay. Yeah, so for the PS40, there were 19 different categories, and the T51-R, there were 16. So it doesn't just say yes or no, does this fit in? It's trying to classify, saying which of these categories does it fit into. And so this giant plot of numbers can be a little bit overwhelming. The main things to focus on are during exposure and within 10 minutes after initial exposure. During exposure was almost perfect accuracy, so when either system was turned on, the model knows when it is. Versus 10 minutes after, you can see right here, essentially 0 correct guesses. It doesn't know if it's within 10 minutes after. T51-R, only 7 correct guesses as compared to the dozens of incorrect predictions. And look at PS40, it almost never guesses before exposure except for when it is, versus after exposure. Looking at the T51-R, it sometimes does guess before exposure, even if it's hours or days afterwards, sometimes weeks. Transformer had a lot of the same information. Again, during exposure, nearly perfect accuracy. Later on, not as perfect. But what you do see is, looking at especially the PS40 along the bottom right area, you can see a lot of yellow values. That's saying, hey, we know it's after exposure, but we don't know how much. It doesn't know if it's 3 days after, you don't know if it's 2 weeks, 3 weeks later. But especially during exposure, you can see obvious predictions being correct. Machine learning analysis. So if you were to use the 19 categories, so this is something that Laura had mentioned, if 50% was just for binary, that would be random predictions, it's just guessing. But for 19 categories, that corresponds to about 5% accuracy if we were to make random guesses. So 50% is actually much more impressive than that. The T51-R dataset, 16 categories, which would correspond to about 6.25% accuracy for random guesses. And what you can see on the right is essentially the weight that was corresponding to each of these input parameters. So on the top, you see time hour, which is time of day, and day of the week. These were by far the most important features because for both systems, it was only turned on during midday on a weekday, especially for the T51-R, which is over the course of three weeks. You don't have any time when it's turned on like a Sunday or at like 3 a.m., some pretty crazy time like that. Least important features, especially the similarity, you see almost 0 weight to it. Feed count and distance from recorder were also relatively low weights. Impulsivity being around the middle. Same thing with sound pressure level. When both models were trained on either dataset and applied to the other dataset, it doesn't do nearly as well. So as compared to the 45 or 55% for either dataset on either model, go down to around 8 or 10% roughly. So that is much less accurate. But when it's trained on the T51-R dataset applied to the PS40 dataset, it's higher than vice versa. So that's essentially what we can assume from that is that anything above that initial 96 kilohertz recording frequency up to the 192, probably learned something in that higher frequency that corresponds to any other patterns in the data set. A little bit of recap. What we've learned from this is PS40 amplitude and periodicity. You see definite correlation between exposure periods and the metrics. The T51-R, kurtosis, and peak count, you see a little bit of habit in that data set. And in general, the transformer performed better than the CNN, both in accuracy, precision and recall, and F1 scores. Couple of limitations. So if I were to have been given more time to plan this in the future, recording frequency was too low, I would try to make it at a higher frequency. So either better sound traps or maybe another bit of hardware. Motion mapping sonar and boat operating not independently. So again, as I mentioned, they're always on at the same time. So there's no time where the boat's moving and the PS40 or the T51-R is not, or vice versa. Weekdays, same time of day. Again, you don't see any time on weekends when they're in operation or at a crazy time in the middle of the night. Limited during exposure period, especially during the PS40. There's only about 3 days of recording pre-exposure and just a few short hours during exposure. So if I were to do this again, I would try to have the PS40 in operation for several different days at different times of day. Larger data sets, trying to do different recording frequencies. So one of the things I would like to have done is instead of just the already low, mid, high, and ultra high frequency, I would have tried to have recorded at the 35 to 45, at least for the PS40, to see if there's any direct and immediate change in that frequency range. More systems recorded. Only one sub-bottom profiler, one multibeam echosounder were tested, and their potential contributions can't necessarily be extrapolated to every other sonar system. Different geographical locations, only 2 deployments, both in the Gulf of Maine. Maybe if they were tried in a place with more, perhaps, biodiversity, more vessel traffic, less vessel traffic, could be some good data set to come from that. And for the hypotheses, it was learned that both the first and second alternative hypothesis turned out to be true. So impulsivity and amplitude were statistically significant comparing during exposure to pre and post. And the transformer did perform better than the CNN at predicting the results. So lastly, I want to thank my committee for all their hard work and time that they've given, and for everyone else who's come here. So thank you. I'd be happy to answer any questions.
Can you go back one slide?
Sure.
We can take questions while I read.
Yeah.
Did you think about trying to look at vessel tracks over your area?
Yeah, so for both data sets, I did have positional data, so I did know when it was like passing by, especially for the T51-R. About a dozen times it was passing over. Versus the PS40, there was really only one time it really went directly over.
Were you able to look at AIS data at all? Was that available for your time period? The period of your thesis, sometimes it takes a while for that to come out.
I did not look into that, no.
We didn't have it. We were getting it from Marine Cadastre. They're kind of,
It's a delay, that's why it's
it's like 14 to 16 months delayed. Hopefully we'll get some, we'll have our own AS receiver on the shoulder.
if you ask NOAA nicely, they might give you data earlier if it's you're like on a grant fund.
That's good.
Yes.
For me, it wasn't quite clear what you were doing with the machine learning models with the neural nets. And so what was your input into that? Because if it was, I don't know, the high amplitude or something like that, then I understand what you're getting out of it is the probability of a high amplitude. But I just don't quite understand what your input to the neural nets were.
Yeah, so each of the soundscape metrics was used as an individual input. So amplitude was one, uniformity, dissimilarity, decount. Those were all, it was essentially tabular data set, so CSV, where each minute corresponds to 1 minute of recording. So that's one individual record, along with the time of day, day of the week, and the spatial information, so the distance from the recorder to the pinging.
Okay, and you fit a different net for each of the metrics that you used, or were they used in a vector combined as a matrix?
So they were all used as their own individual dimension. for both the CNN and for the transformer. So they're both both models were tested independently using the same data sets.
Okay, thank you.
Can you back up? You had a thing with the different importance parameters.
Oh yeah.
That one. This one. So there's the dissimilarity, impulsivity, sound pressure levels, and peak count. Those are the metrics we were talking about putting in as input. The other ones, the time, the day of the week, and the distance that the ship was from the recorder at that minute. It's not clear to me. Did the model get those as input at any point? As input with tests or with the training data? Well, let's break it down. Like when you're training the model, are you giving for every minute that you're putting in to train on? Is it getting all of these numbers?
It is, yeah.
So it's getting the time, hour, day, week, distance. And then when you're testing and evaluating how well the model performs, are you giving it just the soundscape metrics? Or are you giving it the time? Are you giving all of these in when you test a minute?
They're all being used as input, and essentially, what this is showing is like after it's already been trained and tested, trying it again with randomizing each of these features and trying to find out how much accuracy it drops each time. So for like time of day and day of the week, it dropped by like about 20% accuracy, dropped down to like 30 or so. Versus like the similarity, if it was completely randomized, barely lost any accuracy.
So this is showing if you remove or randomize that value, this is how much performance drops.
Correct.
So because your model was the categories, if you back up to this, your categories, are before, during, and then different periods after. I mean, it seems like if you provide with a test file, if you provide the time of collection, it should almost have 100% accuracy, right? I mean, you're telling it when it was collected.
Well, it wouldn't be 100% accuracy, but if you were to give it time of day, it'd probably still make good accuracy. Probably still better than random predictions.
Well, but sorry for jumping in, but there is a point in if the model just learns that the test signal always comes on at like 2 p.m. Now, okay, you get good accuracy, but is the model generalizable to the case that you were hoping it to be applied to? That's an honest question.
Could you rephrase the question?
Sure. So the point that was just raised is like you give it the time as a feature, and then time, you're trying to predict the right kind of time. But the difference is like the time that you give it as a feature is like a timestamp. Like right now it is December 9th at 9:37 a.m. But this time here is in offset to when the event happened, right? So that's, you could argue that there's no data leak because one is wall clock time and the other one is delay since event, which you're trying to predict. However, and I think you kind of found that the time of day is a really important feature to get this prediction right. So what it might have learned is that the damn noise always comes on at like 2 p.m. Now, that's fair. But like if you're trying to use your machine learning model in a case where you don't know whether the event always comes out at 2 p.m., you're trying to identify what is the actual kind of like, what's the response of the animals and so on and so forth. And maybe they might react differently during the day than during the night. Now, if it has just learned that the damn scratching event always comes up at 2, then this will not be generalizable to the case where you're trying to predict the soundscape for scratching noises that come on at any time of day. You know what I mean? So there could be some kind of leak in it just learns. Like for example, if you take away all other features, you only keep the timestamp. So that's what would be your null hypothesis. You could then run the same transformer in CNN, and the question is like, how good is the accuracy of that? And that would be the contribution of just having learned at which time of day the scratching noise just like comes on. And from the delta, you see how much you get actually from your timescape, from your soundscape kind of like data.
Okay. So if it was given just time of day, I could still apply that and say, okay, it's on at 2 p.m. and it's a weekday, we'll say.
Correct.
It will know, I know that it's on because it's a Monday at 2 p.m. It's going to be turned on because from the training data, that's the only time it was turned on.
Correct. So what I'm saying is if you had that model from the difference to that's like sort of like the null model to these numbers that you have here, you could sort of then back out how much you actually have learned about the soundscape, which is sort of then where you don't have any data pollution from some kind of like regularity of like your experimental setup. I'm not suggesting that you do that. I'm just telling you how you would do it if you were to do it again.
Right. Yeah, if I were to do it again, I would try to make it different times a day so that the time of day wouldn't be the only really most important feature. Ideally, it would not be the most important feature.
Yeah.
So the graph you had, don't switch back to it, but what that showed the importance of time of day and date, is that for both of them combined? Was that for a particular one?
That was, I think, for just the transformer on the PS40 data set, I believe. But it was still roughly the same values for either data set, for either model.
Because the PS40, it only was once on one day. So it's only for like an hour on one day. Mm-hmm. But with the T51-R, that was summer hydro. So they were out there, I don't know, a dozen or 2 dozen days. But they were always out there, late morning to mid-afternoon. And it was always on a weekday. And so I think the real problem with that is that you're always getting examples of sonar exposure during the work week,
right?
When fishermen are going in and out and all this is going on. You're not getting examples of it at night when there's less other background noise, and you're not getting examples on the weekend when maybe there's more recreational boaters out or something like that, or they're not running a pile driving rig or something like that. So that's I think a bigger concern with that one. Although I'd be really interested to see how these work if you don't give it any time of day or date information at all, and you force it to rely solely on the soundscape metrics. Okay. And even an interesting test on that would be, just seeing if it can pick out roughly what hour of day it is on a sample by soundscape metric. I imagine it would probably be fairly good at that if you broke it down. Instead of doing these categories, if you just had midnight to 4 a.m. and 4 to 8, stuff like that.
Oh, yeah.
Or is the committee going to have a chance to ask questions after the public portion?
Yeah.
Oh, and then I'll hold that.
Okay.
Yes.
Yeah. Could you go back to the goals slide? I'm just trying to think through.
Yeah. So the first one was trying to essentially find out if there are any statistically significant changes in the soundscape metrics for different exposure periods at different frequencies.
Yeah, I guess part of the question is, well, the overarching question I'm interested in is, is this extra effort to using these models worth it right now? At least that's structured. But wondering, so you fed in these metrics that are meaningful to us because there's something that we can easily look at in the data, and I think that makes sense for interpretability. But how do you think that might have biased things, or is there a different approach where it's kind of a quote unquote non-parametric approach where you say, hey, you figure out what's going on here. Don't. So what do you think about that?
Yeah, so really the first goal was the statistical analysis. The second one was for machine learning. So it was kind of two separate goals, just using the same data. And really what I think about it is both models were definitely useful because they were able to say, like, hey, if one model is predicting much better than the other, is that just an anomaly, or was one random test of that data just a loophole?
Both models, you mean both the machine
learning? The CNN and the transformer.
Right, but
Yeah, if I could, can you step back a little bit and talk a little bit about the purpose of predicting predicting the time since exposure? And like, why go through that effort?
Yeah, so that was kind of building off of the statistical analysis. So if you were to see, let's say amplitude is very high before, and then it drops during exposure, and then it either stays there 24 hours after or jumps back up, the models will be able to see and say, okay, if it's a very low value, we know that it's during exposure. So, and if it's making basically random guesses, that would essentially say there's no change in the metrics.
The idea being that, like, you're trying to produce a model that will predict what the soundscape is likely to do after exposure to one of these sonars.
Yeah, either saying during or after does it change compared to before exposure.
I think what Val's looking
It
for.
says predicting time since exposure, which is different than predicting the response of the soundscape as a function of time. It's just a subtle difference in wording that's a little confusing to me.
It's more like recovery time.
I always saw it as, the way I saw this being framed is if there was some sort of indirect secondary effect, like you blasted this sonar and all the snapping shrimp shut up for 2 days, right? Some sort of direct effect, some sort of effect that it has on the soundscape after the exposure, then maybe we don't see it in line plots. But like maybe if you throw all this data into a machine learning model and it goes, oh, I can tell you that is 2 hours after a sonar was because of whatever it did, some black box thing, then that implies that there's some sort of secondary effect. But if you throw all this into a neural net and it says, I can't tell you whether that was 5 minutes after a sonar or 5 hours after a sonar. It doesn't prove that there's no secondary effect, but it's evidence that there's probably not because like it didn't find anything. So I think that was when I was thinking about it. That's how I was perceiving that. Because I think if you saw the other result, it would be very strong, right? If the machine learning thing was like, ooh, there's definitely 5 minutes after a sonar was blasted because there's no snapping shrimp, right? That would be very strong evidence. But we didn't see that. And you can't tell whether or not that's because the model doesn't work or because there is no effect.
And I think of it as recovery time. If there is no recovery time, it means there is no quantifiable impact. Whereas if there's a long recovery time, it insinuates that there was some sort of impact that the environment needed to recover from to get back to baseline.
Okay. I suppose you could have an impact for which the recovery time is so short, it's really difficult to tell.
Correct. Yeah,
That'd be the 1 minute.
Yeah, that would be less.
So if you were to design this again, you had it had a bunch of data, maybe a little bit more, but essentially everything else was the same. Would you have used any other statistical techniques that might be better at teasing out that time aspect? Because to me, that's not the first thing I would go to find time lag. That'd be a thing I would try later.
Right. So another thing I would have liked to have done is to, as the input data for the models at least, to have used every single frequency range, so low, mid, high, and ultra high frequency. I used the broadband, so between 1 and either 96 or 192 kilohertz. So if you were to say like, oh, we know this happens in the mid frequency, there's something happening there, but that's not where the ship is, or not where the either system is. Versus if you see, oh, ultra high frequency, we can predict this perfectly, you would say, okay, well, it's kind of obvious to say, not obvious, but you can say the PS40 or the T51-R had a big contribution to the soundscape in the ultra high frequency range.
It's an interesting project, I think. To see if particularly a neural network or a transformer network can pull a signal from below the noise floor, if I think about it in an acoustics kind of way. which is a little confusing given its context, but the signal being a response or recovery from a stimulus that you didn't actually observe.
So you used the soundscape metrics as the input to the machine learning models. You know, what are the alternatives to doing that?
To still use machine learning.
Well, yeah, because I think Brian kind of was getting at this. He was saying, you know, why are we using the soundscape metrics as input?
Yeah. So I think another thing that could be done is to look at each individual metric as its own, to use a model on each individual metric. And I could be wrong, I'm sure Laura can correct me, but I believe it's a recurrent neural network that can use one single metric to predict the filter, essentially. Is that correct, Laura? Recurrent neural network?
Well, I mean, not quite. I mean, I think what the CNS does is it always looks back 5 observations or 10 observations or 100 observations, and based on that tries to make a prediction of where we are right now. Where a transformer can just look at anything and has like its own means of like weighting observations in the past to make a prediction.
But I think what I'm getting at is can you just use the 1 minute wave files as the input to the machine learning models?
Yeah, I mean, the machine learning model doesn't really care what kind of data you give it. The question is whether it makes sense to base a prediction on it, whether it will generalize.
But Reilly, like, can you use the wave file? Like, is there a reason we didn't just take the wave file and use that?
The actual sound file?
Yeah, the actual sound file.
I have heard of sound being used as input, but I believe it is sometimes transported like into a spectrogram, so it will use an image instead of the raw sound. I'm not aware of sound being used directly as an input.
Well, that's fine.
Yeah.
All right, well, we're going to cut off public questions just because there's another talk starting in 9 minutes, and then the committee will